Yeah, so the topic we are going to cover today is, as he said, debug signal trace. This is a hardware mechanism to track and capture microarchitectural events in post-silicon, not only for the purpose of debug, but also for coverage and performance analysis. Apart from me, Shanesh and Rahul also worked on this. Unfortunately, they are not here, but you'll see their work through the slides. So let's dive right into it. And I think I have left enough time for the questions, so it'll be fun to have an interactive section. So what are the topics we are getting into, right? So first of all, why do we need something like a debug signal trace? What is the problem statement? And do we have enough ROI of solving this? And once we are convinced ourselves of that, how do we go about implementing the debug signal trace? Once the hardware is in place, how do we go about programming it? So we'll talk about the programming model. And then what are the use cases of this beyond debug? I kind of gave away on that in the topic itself, right? Apart from debug, we can use it for performance and coverage. So we'll cover that as well. We'll get into some implementation details, like what microarchitectural events will be covered, we should cover as part of DST. And then how do we minimize our cost of development? Finally, we'll also touch upon what the RISC-V community can expect from Tenstorrent with respect to this feature. Obviously, we want to make the post-silicon ecosystem very rich for all of us so that we can have rapid deployment of RISC-V. So yeah, so let's get into the first topic, right, which is what is the problem statement, why do we need it, right? So if you want to fast track debug, you need more data, right? Now, the traditional method of collecting data is scan. Think about it. What is scan, right? You run the test, you hit a bug, you don't know whether the bug was hit or not. Then you wait for a system hang to happen, and then you collect the trace data. And what do you get? You get a single snapshot of all the microarchitectural events, right? So in essence, you get what is the hanging state of the system, but you have lost all the transitionary history leading to it. Oops. And sorry, the slides didn't really come out as I thought it should, but nevertheless, I think I can just talk through it. But essentially, you have lost all the transitionary history, right? And when you do a scan and write down, which is the traditional method. On the other hand, you also have instruction trace. And in case of instruction trace, you are able to trace the architectural states of PCs and CSRs. But the thing is that for your visibility is limited to the architecture state. And for this feature to work, you need to also have functional code, right? For debug, what you want is that you want to have a continuous capture of your internal microarchitecture state up to the point of fail, and hopefully also correlate the same with software instructions so that you can have a much faster debug. And that's what debug signal trace aims to solve, right? So now let's see how exactly to go about and implement the debug signal trace, right? So essentially, we can think of implementation of debug signal trace into three parts, right? The first part is, let's see if yeah, there you go. So the first part is really building a blog which will help us select debug signals or hardware signals, aka microarchitecture events of interest, right? What signals you select is obviously going to depend upon your initial post-silicon triage. So, but nevertheless, you need to have a hardware blog to select those signals. So that is what is provided by this debug bus mux tree. Now, once you have that hardware blog to select events of signals of interest, the next thing is that you want to capture the transition on these signals and also define windows of when to start the capture and stop the capture. And then additionally, you may also want to compress the data so as to minimize the memory footprint of trace and also to reduce the bandwidth requirements. And once you have the compressed data, you generate the packet, and now you are ready to ship the packet for storage into memory. It can be SRAM or system memory. So this piece of logic essentially does that. So keep in mind, our implementation is also trying to ride on top of what is already implemented for instruction trace. So we actually share the network between the debug signal trace generator, which is the one which generates the packets for DST, and also the trace encoder. Additionally, we also leverage the trace start and stop events as defined in the RISC-V debug spec. Essentially, we use sgtrig. On top of that, we also have custom logic where we can start and stop events based upon debug signal mask and match. We also have ability to capture periodic timestamp, and I will cover that later why that is important. So finally, once we have all the packet captured, we send the packet to either SRAM or system memory, and using trace funnel and trace sync. Our folks who are familiar with the RISC-V trace control spec would immediately latch on to saying that, oh wait, trace funnel and trace sync is something which we already have, in this in the RISC-V spec or the trace spec. And bottom line is we want to leverage blocks which have already been designed for instruction trace. So this is the hardware for implementing debug signal trace, right? Now, what goes on this? How are these packets? What are the packets which are formed, right? So essentially, we form two kinds of packet. One is data packet, which is essentially debug bus signal values, and then second is timestamp. So we have a header with different fields, and one of the fields is to distinguish between data and timestamp packets. Didn't mean to do that. Let's see. Okay, yeah. We also have a source ID, and this source ID is important when you have a multi-core design. So you want to identify from which core you are collecting the microarchitecture events. We have the trace start and stop info, which basically says when the trace started and stopped. And then I'll cover the packet loss in a minute. But apart from that, we have the payload, which is either debug bus values or timestamp. Obviously, debug bus values is showing the transition on the micro hardware signals. And in our implementation, we have compressed it. And then we also have timestamp, which is sent periodically. Now, coming to packet loss. We also have a dedicated bit to indicate packet loss. And why is this bit important? Because assume for a minute that when you're sending data from the DST generator over the trace funnel to tracing to memory, because of back pressure, you're losing a packet. In that case, you want to indicate that you lost a packet, because when you're tracing signals and if you're trying to make a conclusion that a particular signal transitioned from value A to B, you want to make sure that the packet loss bit is set to 0 so that you can indeed make that conclusion. So that's the significance of the packet loss. Okay, so we just discussed about the hardware. Now, what is the programming model? We have programming model for both DST data capture and data decode. So the programming model, the first thing is that we are trying to reuse as much as possible from the RISC-V control spec. So many of our programming model actually mirrors what is already there in the RISC-V trace control spec, right? But key difference here is that we have steps to select debug bus signals and define trace start and stop events. So once that is done, we run the test and enable the trace. And optionally, we can also enable instruction trace so that if you want to have correlation with software. Right? So in here, we also, when we are enabling instruction trace, we also enable timestamp. And this is where timestamp becomes important, because you can use the timestamp as a common token between debug signal trace and instruction trace to correlate the two. Right? And the rest of the steps is pretty much mirroring what is there in the trace control interface spec, which is basically we poll for trace stop or trace buffer updates, and software will read from either the trace SRAM or system memory to get the data. Now, once you have got the data, now you need to decode it, right? So this is the steps for decoding. You decompress the data in case you have implemented compression logic. You parse the uncompressed data into packet and header fields, and then you start mapping for the debug bus values. You start mapping the values back to the debug bus signals which you selected as part of mux errors. You also want to start sequencing and correlating the traffic using timestamp or the order in which it appears in the memory. once all this ordered set of data is available, you put it in GUI or text view for further analysis. So this covers our programming model, right? So now think about it, right? We are essentially tracking, taking a bunch of microarchitectural hardware signals, aka microarchitectural events, and putting that into memory. This data gives us use cases much more beyond debug, right? You can look whether any design intention was violated. So for example, oops, I should start using the right button here. So for example, if the design intent was that the signal C should not be set if signal A takes a value of D, then that's a clear violation of the design intent, aka sort assertion, right? Also, you can use this data to see whether you are getting the right coverage. If a signal is not taking all the legal values it can take, for example, in this example, signal A is only taking a value of 3 and 1. That means that you have there are coverage holes with respect to the signal. So that indicates a coverage hole which you want to probably you want to complete it with additional stimuli. So it helps you with coverage. You can also do performance analysis by essentially correlating the instruction trace with the signal trace and or even signal trace by itself, looking for places where you see long transition or long deltas between transition of certain signals, and that can give you enough indication of why there are certain performance anomalies happening. So just the ability to dump a bunch of microarchitecture events into memory and doing a post-processing gives you a lot more capabilities than just debug, but also helps you with coverage and performance analysis. Right? So now this feature is only as good as the kind of signals you're selecting when you're building the hardware. So basically, what are the signals you're selecting on the debug bus, right? Now, there are certain do's and don'ts you want to follow with respect to selecting these signals when you're building the hardware. So you want to select signals which are critical, right? Like state machines or request response interfaces or credit token counters. Also, we should probably go with signals which have a wider footprint so that with that particular signal, you're probably covering multiple features. Another way is also basically talk to your pre-silicon guys and say that, okay, what are the RC files your guys are using for your waveform analysis, and look for popular signals from there and use that in your debug bus. Now, what are the don'ts, right? Avoid data bus is no good really. And then also some signals have the tend to appear in multiple blocks multiple times, and so avoid trying to repeat capturing the same signal from different blocks. So yeah, so summary, you want to follow certain best known methodologies for selecting debug bus signals so that you're selecting the right set of signals. Okay, we have more. Okay. Finally, we also wanted to leverage, I think as I was talking from the previous slides, we want to leverage as much from the trace control interface spec. This not only uses our implementation, as I was explaining earlier, with respect to trace run and tracing, but also helps with ease of adoption and also helps our software debug vendors to rapidly develop software for debug signal trace. So this reduces our overall development cost. I have a backup slide which says what are the registers which are mirrored pretty much between instruction trace and debug signal trace, and pretty much all the registers are mirrored. Okay, finally, what is the additional things which you can expect from Tenstorrent? We think this debug signal trace is a very useful and powerful tool for post-silicon. We want to really see how we can share our design and also work with software vendors in providing software stack for debug signal trace. Additionally, we will also be working with the RISC-V debug work group and see how we can standardize it. So that concludes my presentation, and I think we have some time, at least more than 3 minutes for questions.
Yeah, questions? Oh, hang on, Robert. Oh, one here first.
Go ahead, Deborah.
Oh, you're in here.
Okay. A high five, great presentation. This is real silicon stuff. 2 questions. How many cycles can you support, record, and what's the overheads, area, power, timing costs?
Yeah, so the number of cycles which we can trace really depends upon multiple factors. So one is the depth of your trace SRAM. But if you're tracing the data into the system memory, the number of cycles is really large, right? But if you put your trace SRAM in a kind of a buffer mode, it really means that how many last number of cycles you want to select, right? Now, we can go with simple math, but here what the math depends upon the depth of your trace SRAM in case you are going into wraparound mode. But additionally, it also depends upon what compression logic you are using, right? So we had, when we looked at the debug bus signals which is selected, we kind of had three profiles, like profile with very active traffic, profile with kind of medium, right, and profile with low traffic, right? And so the normal use cases of a debug bus traffic with a medium kind of traffic, and with our compression, we are able to reduce that, reduce the memory footprint by 70%, sorry, by 30%, right? So yeah, it's a long-winded answer, but if you want, I can share specific numbers with you, but it all depends upon multiple factors. But do keep in, contact me for specific calculations.
Yeah, great question. I'm Entre's chair, and we really welcome this addition, and I think we should try to push it through ratification.
Thank you.
Great work, and I appreciate it. Just for everybody else, the Entrace itself provides a way to add custom packets. There's room for custom, but also a lot of room for standards. So we can just sneak it into same flow. And of course, you can disable trace and still have only this stuff, right? If you want, right? But that's great. And thank you very much for great.
Yeah. So we did look into VDMs or the vendor-defined messages. I can take it offline why we didn't specifically go with the vendor-defined messages, but separate trace packet. But yes, all of it can be done. Totally agreed. Any other questions?
We have more time. No questions? No? That's it then. Thank you very much.
Oh, I think there's a question.
There's a question there?
It was the part two from mine was overheads.
Okay. For the CPUs we are designing, this was really, frankly speaking, a noise, right? So, but the value add we get out of it is large. The largest, where I had to really talk to my physical design team and have kind of some bargaining was with respect to how deep my trace SRAM should be, right? Yeah.
I think that's it then. Thank you very much.
Thank you.